Broadcast is now starting. All attendees are in listen-only mode.
Good day and welcome to the February Pacific Northwest Drought and Climate Outlook webinar. Happy New Year, since this is the first time we're interacting in 2023. My name is Britt Parker and I'm with the National Integrated Drought Information System. This bi-monthly webinar series is hosted by NIDIS, the USD Northwest Climate Hub, and Oregon Climate Change Research Institute. It is designed to provide partners and other interested parties in the Pacific Northwest with timely drought and climate information. Each webinar will be tailored to reflect the current, recent, and forecasted conditions and climatic events, but will also include discussion of observed impacts and other relevant updates from across the region. Webinars and recordings and other supporting materials will be posted on drought.gov later this week. Note that after today's webinar, you will have the opportunity to provide feedback that will help us improve this webinar series, so please take a moment to tell us what you think. Today's speakers include the climate recap and current conditions with Zach Hoylman from Montana Climate Office in the University of Montana. Brett Bauer will talk to us about the seasonal conditions and climate outlook from the National Weather Service Weather Forecast Office in Seattle. We'll then have a presentation on Snow 101, how it's measured, how we monitor it, common confusions and impacts from climate change with Janelle Christensen of the USDA Northwest Climate Hub. And we'll wrap up with a Westwide Drought Tracker Demonstration from Justin Chambers with the Western Regional Climate Center and the Desert Research Institute. Before we begin the presentations, we wanted to highlight the partners who make this webinar series possible. The Northwest Climate Hub develops and delivers science-based, region-specific technologies and practical information that will assist agricultural and natural resource managers with climate-informed decision-making in Idaho, Washington, Oregon, and Alaska. Visit the website listed to get more information, and I'll also put this in the chat box in a few minutes. The Oregon Climate Change Research Institute is a network of dozens of researchers at Oregon's public universities that work closely with other public and private entities. OCRI is housed at Oregon State University. OCRI advances understanding of regional climate impacts and adaptation and cultivates climate-informed communities. NIDIS was established in 2006 by public law with a mission to improve the nation's capacity to proactively manage drought-related risks by providing those affected with the best available information and resources to assess the potential for drought and to better prepare for, mitigate, and respond to the effects of drought. NIDIS is building the foundation of a national drought early warning system through the development of regional DEWS, where networks of partners and stakeholders share information and actions that help communities cope with drought. While the ultimate goal is a national early warning system, we recognize that impacts and early warning information differ across the regions. Each DEWS has many of the same base ingredients, but ultimately have their own flavor to reflect the needs of their region. The Pacific Northwest DEWS was officially launched in February of 2016, and our strategic plan and information on current activities are available on drought.gov. To facilitate our early warning system, more precipitation observations are needed. We encourage you to join COCORAS, the Community Collaborative Rain, Hail, and Snow Network. This is a unique, nonprofit, community-based network of volunteers of all ages and backgrounds working together to measure and map precipitation, rain, hail, and snow, as well as condition reporting. Observations by COCORAS observers of precipitation events or the lack thereof are important to capture and improve our understanding of weather. To become a volunteer or learn more, visit cocoras.org or contact your state coordinator, and we'll put those names and email addresses in the chat box. We wanted to highlight that the 6th Oregon Climate Assessment is now available. This is the latest in a biennial assessment of state climate change science, including biological, physical, and social science, and the likely effects of climate change on Oregon. This 6th assessment builds on the previous assessments by continuing to evaluate past and projected future changes in Oregon's climate and water supply. Like the 5th assessment, it is structured with the goal of supporting the state's mitigation planning for natural hazards and implementation of the 2021 Oregon Climate Change Adaptation Framework. And finally, I just want to highlight that the third annual Pacific Northwest Water Year Impacts Assessment will be forthcoming soon. So watch your emails and we'll get this out to everyone as soon as it is released. And with that, I'm going to turn it over to our first speaker, who's Zach Hoylman. And just give me 1 second. We were having some audio issues. Let me try to get Zach. Okay, Zach, go ahead and speak.
Yes, can you hear me, Britt?
Perfect. Yes, we can. And let me get your presentation up. Give me 1 second.
Great, thank you so much.
Okay.
All right, well, thank you, Britt. And once again, my name is Zach Hoylman, and I'm the Assistant State Climatologist in Montana and a Research Assistant Professor at the University of Montana. And I'm excited to be here today to kick off the climate and current conditions recap of the Pacific Northwest. Drought, as you all know, has been a persistent feature of this landscape starting in about early 2020. And while it's been unseasonably cold the next several months, much of the area has received below average precipitation, especially in the short term. And long-term precipitation deficits remain large across the entire area, most of the area. So my presentation today will focus on how conditions that we've experienced over the last couple of months compare to historical conditions. And specifically, I'll focus on the last 90 days of precipitation and temperature, the last 30 days of precipitation and temperature, current snowpack, soil moisture, and stream flow conditions, and how all of those constitute our current depictions of drought across the region. I'm going to attempt to complete all this in the next 10 minutes and then hand it off to Brent for a discussion of our seasonal outlook. Okay, so let's start with 90-day anomalies. So over the last 90 days, we've seen anomalously cold and relatively dry conditions. So in this slide on the left, I'm showing you the temperature departure from normal over the last 90 days compared to the 1991 to 2020 climate normal. White to blue shading represents cooler than normal temperatures, while red shading indicates warmer than normal conditions. Overall, as you can see, there's essentially the entire region has experienced cooler than normal temperatures over this time period, and there's no red on that map. These deviations from normal range from about 1 to 6 degrees below normal, which is considerable, especially over a 90-day time scale. The figure on the right shows our anomalies in precipitation over the last 90 days. Increasingly brown areas represent below normal precipitation, white areas represent normal precipitation, and green areas represent above normal precipitation. I'll call your attention to the area of brown from north central Oregon extending northward along the Washington coastline and along the western portion of Idaho. Here, precipitation has been well below normal, with only 50 to 90% of normal precipitation falling over the last 90 days, though some locations are only slightly below normal. On the other hand, eastern Idaho and central Washington have experienced slightly wetter than normal conditions, and in some places even much wetter than normal, with values ranging from 110 to upwards of 200% of normal. All right, next slide, please. As we transition for the last 30 days, we can see similar temperature patterns across the domain. Starting with temperature on the left, you can see the entire domain has generally experienced below average temperatures ranging from roughly normal, for example, across large portions of Washington, to a whopping 12 degrees cooler than average in Idaho. And more specifically, southern Idaho has generally experienced the most dramatic temperature anomalies, with Idaho Falls falling about in the center of this cold anomaly. Shifting to the right, once again, precipitation deficits over the last 30 days show much drier than normal conditions across the entire domain, besides western Montana, that is. Large portions of the domain have received only 5 to 25% of normal precipitation over this period, especially in Oregon, which is indicated by that dark brown. According to NCEI, this last January was the 20th driest January on record over the last 128 years, and that does not include February. I would expect February rankings to be similar, if not drier. Next slide, please. So how have these cool and relatively dry conditions impacted the snow accumulation season? Well, on the left, I'm showing you the percent of average snow water equivalent, or SWE, for February 23rd across the mountainous regions of the Pacific Northwest. These data are measured using snow pillows at snowtel sites across the Rocky Mountains and Cascades. You can think of snow water equivalent as the amount of water that would exist as a depth if we were to melt the entire snowpack at a point. And on the right, I'm showing a slightly different estimate of SWE anomalies, calculated using a snow model maintained by NOAA called SNODAS. Let's start by looking at the snowtel data. The left-hand figure shows the average snow water equivalent for each HUC 6 or hydrologic unit code 6 watershed. Yellow and orange shading indicates below normal snowpack condition, green indicates normal conditions, and blue indicates above normal conditions. As you can see, the snow accumulation season has generally been on track for what we would expect to see for this time of year. Almost all basins are near normal as far as SWE goes for the date in question, with the exception of the northerlymost sections of western Montana and 2 basins in western Washington. Snowpack is somewhat above average across portions of southern Idaho. Let's shift to the right-hand figure now and look at the SNODAS data set. SNODAS is a model that takes an assimilation approach to estimating snowpack dynamics, leveraging both a snowpack model as well as observations from SNOTEL data and other instruments. The main difference here compared to the SNOTEL map on the left is that SNODAS estimates snowpack across the entire basin, low to high elevations. Here we can see a similar story to SNOTEL, where snowpack is generally at or above normal, shown with those cooler blue colors. However, this model is indicating that some mid to low elevation snowpacks are starting to fall behind slightly. But overall, the snowpack conditions shown here are relatively decent given the general lack of precipitation over the last 30 days as shown before. Next slide, please. The persistent drought conditions continuing from the last several years in conjunction with the lack of significantly above precipitation over the last few months set the stage for average to dry soil moisture conditions across the Pacific Northwest. In this slide, I'm showing NASA's Short-Term Prediction Research and Transition Center, also known as SPORT, modeled soil moisture percentiles for February 24th. And on the right, we're looking at the U.S. Forest Service soil moisture product TopoFire, which is also another soil moisture model. Starting with the plot on the left, red colors represent below average conditions, while blue colors represent above average conditions. As you can see, soil moisture is generally below average in the western and central portions of the domain, especially in central Oregon and north central Idaho. There are some locations with wetter than average soil moisture conditions in Idaho as well, but they are relatively spatially limited. Shifting to the right, the TopoFire-based soil moisture anomaly estimates are generally similar, but negative anomalies in Washington and Oregon are farther to the east, and soil moisture anomalies are much more negative in Washington. Overall, this is a reflection of both long and short-term dryness. Importantly, dry soil moisture anomalies represent a sink for spring moisture and snowmelt, which may have an influence on streamflow dynamics come spring. Next slide, please. So looking directly at current streamflow conditions now, here's a map of USGS stream gauges and flow rankings across the Pacific Northwest over the last 28 days. Across the gauge network, blue symbols indicate greater than 90th percentile flows, or high flows for this time period, or well above average streamflow. Light blue is between the 75th and 90th, green is the 25th to 75th, orange is 10th to 25th percentile, and red is below the 10th percentile, or well below average. Generally, as you can see, the majority of gauges across Washington, Idaho, and Western Oregon are recording below to well below normal stream flows, with a few exceptions. Streamflow conditions are generally low in the western portions of Oregon and the southwestern portions of Washington and across southern Idaho along the Snake River. So overall, streamflow conditions are relatively low. Next slide, please. So summing all these observations up, let's take a look at last week's Drought Monitor map updated by Richard Heim. As you can see, drought continues to be a persistent aspect of this landscape across the Pacific Northwest, despite the cooler than average conditions over the last several weeks. Low stream flow, dry soils, and precipitation deficits over the last 3 to 24 months and even longer have produced widespread regions of severe or D2 and extreme or D3 drought conditions across Oregon. There's also a section of Oregon that is currently in D4 or exceptional drought conditions, which is the most severe drought class. As you will see in the next slide, drought improvements have occurred over the last several weeks in Washington, leaving only abnormally dry or D0 conditions in Idaho and western Montana. It's also important to note that that 2 county-level drought declarations in Oregon were issued last week in Crook and Jefferson counties, citing extreme conditions over the last 36 months. And in summary, the current drought in the Pacific Northwest is widespread, long-standing, persistent, and far from over. Well, can you go back one slide real quick, Britt? And just real quick, let's take a moment more directly to examine the recent trends in the USDM. On the left, I'm showing you a 3-month change map of the USDM classes, and on the right, a 1-month change map. Starting on the left, you can see the drought has generally intensified across Western Oregon, Northern Idaho, and Northwest Montana over the last 3 months. However, drought has been ameliorating across most of Washington, along with the southern Oregon border, and across parts of Idaho. More recently, conditions have been degrading slightly, likely in response to recent severe precipitation deficits. Next slide, please. And in conclusion, I just want to summarize some of the findings here. When we look at temperatures, it's been pretty much cooler than normal over the last 90 days across the majority of the Pacific Northwest, especially in portions of Idaho. And the last 30 days have been more moderate, but still show below average temperatures. Precipitation, we've had 90-day precipitation anomalies have been generally drier than normal, especially along the northern 2/3 of Oregon, Western Idaho, and Western Washington. And there's been significantly less precipitation than normal over the last 30 days across Oregon, Washington, and Idaho. And these conditions and recent deficits have been contributing to reduced soil moisture, as I showed you in those 2 different soil moisture models, reduced stream flow, especially across the Washington, Oregon Cascades. However, one glimmer of hope is that snowpack is showing encouraging accumulation so far, but we have a long way to go before melt, so it's too early to say how that's all going to play out. And thank you very much.
Great, thank you, Zach. I am going to turn over the presentation to Brent, but I want to just pause before Brent, you start. And Zach has to drop off a little early, so I just want to give everybody an opportunity to type any questions into the chat box for Zach. And I noticed there was, let's see, one, can you comment on the significant discrepancies in the spatial extent of dry soil moisture between the 2 models you showed? How do these very different estimates validate?
Yeah, that's a really great question. And we've done a pretty extensive soil moisture validation analysis, and these 2 models typically tend to be the most accurate when describing soil moisture conditions. That being said, TopoFire, the one on the right, is more kind of one of the specialties that it attempts to emulate is kind of dynamics in the high elevation mountainous regions. And so I think that maybe why we're seeing so much higher soil moisture anomalies, dry soil moisture anomalies in those mountainous regions might be due to a better representation potentially of soil conditions and those kind of rocky soils up in the high elevations. But it's really hard to say. It could be due to many different things, but in general, some of the most dramatic differences between these models tend to be soil conditions. I think there should be more research to be done to understand these differences, but in general, it's most likely due to its interaction between soils and vegetation.
And then, Zach, we have a couple questions related to Oregon. So I'll ask them, but if you don't feel comfortable, on some of these Oregon very specific questions, I'm happy to also tag in Larry O'Neill via email.
Sure.
One is, can you talk about the drought conditions in Crook and Jefferson County, which according to the latest Drought Monitor update is still under extreme and exceptional drought? How are the drought conditions there faring in historical context? And would the recent precipitation help this week?
Yeah, sure. I think that's a great question. And what's really happening, as far as I understand, and looking at a lot of different data sets across Oregon, so Oregon's been dealing with really long spread kind of periods of precipitation deficits. So we're talking about up to 3 years of precipitation anomalies that are driving a lot of these drought conditions that might be reducing stream flow dynamics like we were showing, and groundwater availability, et cetera. And so, while these recent precipitation events, I think, help, of course, in the short term, there's a lot of ground to be made up because we're really looking at multi-annual drought conditions across Oregon that are really driving this. And so, like I said in one of the slides, during those declarations, they were really citing the last 3 years of precipitation and evapotranspiration being some of the driest on record, and that's a record going back to 1895, I believe. So conditions are very, very extreme, especially when you're looking at those really, really long time scales. So the short-term precipitation is likely to help, but is not likely to eliminate drought, would be my interpretation.
Great, thank you. And one other, a notice of a wet bias in southern Oregon across northwest Josephine County, extending north to Coos and Douglas County lines. I believe there's maybe a data problem there. It's been showing up in that area for at least a year. I don't know if you can comment on that, Zach.
Yeah, I don't think I can comment on that directly. By wet bias, I assume you're speaking to the models are suggesting things are wetter, or they've been receiving more precipitation than normal, or than is actually recorded at stations, is how I'm assuming you mean what you mean by bias. And it's hard to say. Modeled products have their limitations. Generally, they do a pretty good job of replicating precipitation anomalies across space, but sometimes they can fall short, especially with really extreme precipitation events that might be kind of driving the accumulations. For example, you could have a big precipitation event that occurs over a really short time period that may not impact conditions as much as they suggest from the models. So it's kind of hard to say in terms of what's going on up there, but if you wanted to follow up with me, I would be happy to look at the data and try to give you a clearer answer.
Great. And then one last quick question. Is low stream flow along the coast due to low precipitation or colder temps that are keeping precipitation on land as snow and ice?
I think it's probably, this is the low flow season, right? Typically when we're going through the kind of the deep parts of winter, we're already in low flow conditions. And so these are all percentiles. So when I was showing you those stream flow gauges, that's the last 28 days with respect to that same 28 days on record. So it's even lower than we would expect for the low winter flows that we would normally expect. So I think that's probably driven by long-term precipitation deficits that are impacting things like groundwater dynamics, which are really, what we're looking at this time of year is base flow conditions, and that's usually water that's being discharged from the groundwater system. But, some of the models, example, the sport soil moisture anomaly models are showing that soil moisture conditions are likely to be much below average in these portions of Western Oregon. That might be contributing to these low flow conditions, but ultimately, it's a watershed to watershed basis in terms of what's driving that specific basin's low flow. But I would assume it's a combination of precipitation, long-term precipitation deficits, soil moisture conditions, and groundwater dynamics, and probably late melt conditions due to cold temperatures. So all of the above, I suppose.
Great, thank you so much, Zach. I'll turn it over now to Brent.
All right, thank you, Britt. So as we look at the climate and drought outlooks, I wanted to put something in mind just as far as how the outlooks have been performing so far this year. And so Zach did a good job of showing the differences and changes in the climate signals and what's going on there. So I wanted to back out just a little bit and take a little more, a larger view of the entire West. Because if you'll notice, in our area, Pacific Northwest, there was some improvements in some places where it worsened. But the dramatic improvements have taken place south of here. And typically what we expect and had seen in the outlooks for a La Niña year is colder, wetter in the north and warmer, drier in the south. And we've been getting the storms, but they've been sliding through our area pretty quickly, but hammering down south. And I'll touch on that a little bit more later. Go back up. So let's take a look at the La Niña status. We still have a La Niña advisory. We still have La Niña present because we're still below normal on the sea surface temperatures, and the atmosphere is still consistent with that. Although I'll say, as I mentioned, the impacts have not been as consistent with that. And so neutral conditions, conditions are expected to begin within the next couple of months and persist through spring and early summer. Let's take a look at the values. You see, for Pacific Northwest, the Niño 3.4 area of study is right at -0.5, so right at the threshold of La Niña. And if you look kind of east to west in those Niño boxes, 1 and 2 have already have been warming and have already gone to above normal. In Niño box 3, it's warming sharply and is basically neutral now. And in our interest area of Niño 3.4, it is definitely been on the warming trend. We're just about to the threshold there. So looking at the probabilities of where we'll go from here is to expect a transition from La Nina to ENSO neutral coming in the next month or so. The probabilities are above 80% by the time we get to the February, March, April, which we're in now, and even higher, above 90% as we get into the next 3-month period. This picture kind of shows going to ENSO neutral, and then in the early summer, and then during the summer, there's greater chances, greater odds now of transitioning to El Nino. So I know Andrea showed this snow water equivalent in La Nina slide up in the graphic on the upper left, and I just wanted to compare that with what the snow tells have been showing of what we do have. Like we said, normally we do expect to see greater than normal snowpack and snow water equivalent in the Pacific Northwest. And although it's not bad, like Zach was talking about, we're kind of hanging in there. There's a few places that are below normal, but look at south of here. They have really flipped the tables for a La Nina year for them. So, like I said, we have been getting the storms, but it's kind of just been barely enough to keep pace in our area, while really ramping up to our south. And I think the fact that we've had the cooler than normal temperatures have helped prevent us from dropping into the below normal, because it's helped the snowpack, particularly on the west side of the Cascades, the snowpack accumulation, because it's been colder and we've gotten more snow than sometimes we do get rain. And also it's helped preserve it by keeping it cold and keeping it locked up in snow and ice. So what are we going to continue with La Nina-like weather? To some degree, the next week we're looking at certainly continuing our below normal temperatures. Those really high probabilities for that. Not as much for the precipitation, in fact near normal for much of the Pacific Northwest, but some of it's still showing greater odds above normal. Going out to the weeks 3 and 4, we do see continuation of that. Cooler than normal and wetter than normal, really pretty much throughout the Pacific Northwest. The month of March as a whole also shows very similar, greater odds of below normal temperature and above normal precipitation. So that's looking good to continue snowpack building and retention. And then finally, when we get to the 3-month of the next one coming, March, April, May, you start to see that cooler than normal odds shrinking north and lessening, and the greater odds of precipitation have pretty much disappeared, and we're at equal chances of above or below or normal precipitation as we get through pretty much the spring months. The drought outlook, the monthly outlook was that's current is out. It's still just for February, and so we're done with February. It was a little optimistic with some drought improvements. That may not be true for the monthly outlook for March. We might not be seeing that improvement being shown. But this is still valid for the 3-month. It was back in mid-February, but it goes through May, through the end of May, and still expecting really some improvement throughout the Pacific Northwest, where there is drought issues right now. So that's a positive look for that. As far as wildland fire, this is not really the start of our fire season for the Pacific Northwest, and so you see pretty much all the West is just normal for March, same thing for April, and same thing for May, which is as far out as they go. So right now, the areas that have been tracking above normal, particularly in the south, are what we typically expect. So far, there's no real indication that of anything unusual yet for our fire season either. So now, kind of taking the sum of the outlooks and what's currently happened, the snowpack, the rainfall, as far as how is that going to impact the water supply and water flow over the spring and summer. So it's kind of a mixed bag. The western parts of Pacific Northwest, west of the Cascades and in the Cascades, are looking fairly decent. There's some scattered areas where it's slightly below normal, a little bit more so when you get further south into Oregon, and particularly southern Oregon. On the just east of the Cascades, then you do see a lot more areas where there's 75 to 90%, or even 50 to 75%, even lower in a few spots, particularly again in Oregon, but pretty much through Washington as well. Then as you get into northern Idaho, well, Idaho in general, that's a little bit more of a mixed bag again, where some places are above, some places are below. But a lot of the western Montana is looking at below normal stream flow and stream volumes for the water supply. And this is for most of the summer. This is the April through September. And then finally, when you get kind of down in the very eastern part of Idaho there, and as part of the basins that flow in there, there's a little bit another area where we see greater than about normal, either plus or minus, but right around normal stream flow volumes predicted there. So there are some places that could be challenged, but overall it is not too bad and somewhat expected given what our kind of mediocre snowpack is looking at. So let me summarize. The drought conditions have improved in some areas like Washington and Eastern Oregon, and worsened in others like Northern Idaho and Western Oregon and Western Montana since we last talked a couple months ago. La Niña is diminishing and will likely be in neutral conditions over the next couple months, within the next couple months, and probably for most of the spring and early summer. This last of three La Niñas has not really looked typical in terms of snowpack and storms, with just modest snow in the north, much heavier snow and rain as well in the southern part of western part of America. So it's kind of, again, flipped the typical outlook that we usually expect out of La Niña. The general outlook is for cooler conditions to persist a little while longer. The wetter conditions persist for now, but will be waning into spring. Wetter than normal, I should say, and cooler than normal. And then continued drought improvement is the outlook for most of the Pacific Northwest, so that's a good sign. And then the wildfire outlook is pretty much just neutral. And that is the rest of my slides.
Awesome. Thank you so much, Brent. Are there any questions? We can take one here as we transition. Any questions for Brent? Okay, I'm going to transition to Janelle. Let me take one more look at the question box. Here we go. So there's a question about where is the divide between north and south?
All right, so how I was speaking to that was pretty much the, let me see if I can get back to a map here.
And she followed up for modest versus heavy snowpack.
Yeah, so the Pacific, our Pacific Northwest DEWS, we're talking about Washington, Oregon, Idaho, Western Montana, excuse me. And remarkably, if you see the transition from kind of the near normal to the well above normal snowpack in the blue versus the green, it's right along, California, Nevada, Utah border with the Pacific Northwest, along there of Oregon. So I was using our Pacific Northwest geographic area, and it just happened to the snowpack just has remarkably happened to line up right along that border as well.
Thank you. Janelle, I'll turn it over to you.
Okay, good morning. You can all see my screen, right? Yes, okay, great. My name is Janelle Christensen, and I'm a climate change communication fellow with the Northwest Climate Hub. Today, I'm going to give a brief overview of snow in the Northwest, how it's measured, how it's monitored, some common confusions, and how it's being impacted by climate change. Snowpack is one of the most important resources in the Northwest, both economically and ecologically. In the West, the mountains act as a natural reservoir by collecting snow in the winter and releasing it in the spring as temperatures increase. Between 60 and 70% of water supplies come from snowmelt. Snow is a critical resource and supplies water to wildlife, farms, forests, and communities. Knowing how much water will come from snow on an annual basis is important for both short and long-term planning for humans and wildlife. So the most common way to measure snow for management is using snow water equivalent, or SWE. Throughout the winter, different storms bring different types of snow, so snow depth does not translate directly to the amount of water held in snow. The differences of snow density can be clearly seen in the picture on the left, and the graph on the right shows the large variability in how much snow 1 inch of rain creates, from between 100 inches for very cold storms down to 10 inches for warmer storms. Because of this variability, SWE is a more reliable metric to use to understand water supplies than snow depth. There are several ways to measure snow. One of the main ways of measuring snow is using SNOWTEL, or snow telemetry sites. Snow monitoring with SNOWTEL is conducted by the NRCS Snow Survey and Water Supply Forecasting Program. These stations measure SWE, precipitation, and air temperature. Some measure snow depth, soil moisture, wind speed, humidity, solar radiation, and air pressure. SNOWTEL stations use a snow pillow, which is the gray circle in this picture, which measures the weight of snow with a pressure sensor to determine how much water is in snowpack. Snow light stations use the same network, but typically only measure snow depth and temperature. SNODAS, or Snow Data Assimilation System, which was created by the National Oceanic and Atmospheric Administration, or NOAA, is a model which integrates snow data from several sources. It models SWE, snow depth, snow temperature, snow melt, and snow density at a 1 kilometer squared grid density. Now let's look at a few ways to understand snow metrics. First, I'm going to discuss 30-year normals, as many hydrologists use them to understand how each year's snowpack compares to historical values. Normals are updated every 10 years. Currently, snowpack is compared to the 1991 to 2020 median. The 30-year normals are based off of the median rather than the average to account for abnormal storms or seasons that may skew the average higher or lower. Normals help compare how conditions are changing across decades and help update water management protocols in managed sectors like recreation and transportation. This is a graph of the 30-year normals. In this graph, we can see that the gray lines are the 30 years from which the red line is determined. There are several important metrics on this graph. First, the peak. For the peak, both the timing and the amount of SWE at the peak are important. The timing of the peak allows us to see if the peak comes around the same time, earlier or later each year. If it comes early, it can affect how water supplies need to be allocated for agriculture, fish, recreation, and others. The amount of SWE at the peak, both above and below normal, can affect water management. Higher than normal might mean more springtime flooding, and lower than normal might mean limiting water supplies to users. Another important metric is the timing of snowmelt. Because snowpack is a natural reservoir, the timing of snowmelt can affect everything from water supplies, wildfire potential, soil erosion, especially if the rate of snowmelt is faster than normal, wildlife habitat, and agriculture. Delayed snowmelt can sustain rivers longer in the summer during drier times. The median meltdown date allows managers to know if it's early, late, or on time, and helps managers understand to ensure that water is adequately stored and delivered to those that need it. Lastly, snow season length from onset to meltout is important for winter recreation and habitat. A shift in the length of snow season could cause a shift in the species that live in that area. Another way to view SWE is with water year graphs. In these graphs, we can look at the important metrics from the 30-year normals and compare them at each site. These graphs are helpful because they also show total precipitation for the year. This could be important if an area is experiencing snow drought. Snow drought is lower than normal water and snow despite precipitation being normal. This could mean that more precipitation is falling as rain rather than snow, as can be seen in this graph of the Snowtell site at Aneroid Lake in 2018. If an area is in snow drought but is experiencing normal precipitation, it can impact reservoir management and can have widespread implications for people and animals that rely on snow. The map of percent of normal is helpful for monitoring current conditions. It's important to note that the map compares the SWE in each basin on the date the map was made to the historic median of that same date. Higher than 100% indicates that the basin is above the median on that day, and lower than 100% indicates that the basin is below the median on that day. To monitor snow accumulation and snow drought, the total volume of snow accumulated over the winter is more important than the level on any given day. These maps are helpful to see variation among basins for the state in comparison to historical information. Now I will discuss some common confusions. Early and end of season snowpack can lead to confusions, especially when using the NRCS percent of normal map to view conditions. In this figure from July 1st, 2022, at the Mountain Hood test site, the conditions for the basin were greater than 150% of normal. If we just looked at this map, we might assume that the area had a record snowpack for the year. Note though that the median for this site on July 1st is 0. To better understand how significant the snowpack at this site is for the year, we can look at the water year graph. When we look at the water year graph for the same station, Mountain Hood test site, it becomes apparent that the snowpack isn't much higher than normal. The peak of snowpack occurs later in the year, which means that on the day the map was made, snowpack is higher than normal, but only because it's being compared to the median of July 1st, which is 0. When comparing snowpack to the drought monitor, it can be confusing to see that there's heavier than normal snowpack, but that drought is persisting. This is most likely because the area was already experiencing drought, and even with higher than normal snowfall or precipitation, that has not yet made up for the historical lack of water. The snowpack will help reduce drought conditions, but not enough has fallen to remove all drought. So now some climate change impacts. There are 3 main impacts that climate change is having on snow in the Northwest. The first is that throughout much of the region, total snowfall is decreasing. This is likely because of increased temperatures causing more precipitation to fall as rain rather than snow. Because of the region's dependence on snow as a natural reservoir, this could have widespread impacts on humans and wildlife in the region. The second impact that is being seen is a change in the date of peak snowpack throughout the region. This is likely the cause of increasing temperatures. This could have large implications on agriculture and animals that rely on the timing of snowmelt in the spring. Lastly, we are seeing changes to the 30-year normals. Because new normals are calculated every decade, we compare snow levels to data from the previous 30 years. This means that as snowpack changes with climate change, so as what is considered normal. In this graph here, we can see an example of a site where the 30-year normal has decreased between the 2 periods. When we compare the black line to the 2 red lines, it's a lower percentage of the 1981 to 2010 normal, which is the dotted red line, than it is for the 1991 to 2020 normal, which is the solid red line. For the sites where normal levels of snowpack have been decreasing throughout the region, something that is 100% of normal now may be much lower than the historic normal for that Snowtell site. These changes mean that water managers need to adjust water allocations to these new normals. So some key takeaways is that snow is important for water supply in the northwestern US. There are several ways to measure and monitor snow, each of which provides slightly different contexts for managers. Some common confusions often happen when looking at the percent of normal map for early and late season snowpack. It's important to remember that percent of normal map is comparing the value of the current day with the historic median of the same day. It does not show cumulative totals in the same way water year graphs do. It's also important to remember that drought can persist even with a heavy snowpack. Climate change is impacting snow in the Northwest, which will have impacts on water supplies for humans and wildlife, wintertime recreation, and water management, among others. Thank you for listening, and if you'd like some more information about SWE, check out our article at the Northwest Climate Hub. You can copy down this link here or scan the QR code to read more. Thank you.
Great, thank you, Janelle. And I also put the link in the chat box as well if you're looking for it. As we transition to our final speaker, any questions for Janelle? And remember, you can always type your question in and we'll grab it at the end as well. Okay, I'm going to go ahead and give presenter to you, Justin. And we're going to have a demo of the Westwide Drought Tracker.
Thank you, Britt. Thank you for the opportunity to show off what we've been working on here at the Western Regional Climate Center with thanks to NIDIS and to the California Department of Water Resources. We've just released a major upgrade to our Westwide Drought Tracker, and I'm going to spend a couple of minutes demoing what this new application is doing. So, of course, there we go. So we start off with a climate dashboard, and we arrive at the continental United States as our boundaries here. We have sections for temperature and precipitation departures, as well as rankings. We also do standard indices and Palmer indices to give a comprehensive overview of drought tracking. You can also switch your boundary if you're interested in a subdivision of CONUS. That is a click away. And for each section, we have different time scales. So if you want to look at that 90 days that we saw earlier, this would be 90 days ending in January. So slightly different than with the February information. The thing that is a real change to the approach is that for the first time that I've been able to see in climate tools, we've been able to access the data, not just the color scheme in these maps. And so these maps are interactive, so you can click on a region here and get not only the color-coded information, but the actual number that you would like to know if you were interested in making some analysis on the data. As we expand this application, we want to provide actions so we can not only see what this number is, but then maybe do a time series on this grid point and see how it's been performing in other Januaries, for example. So, but first we have to unlock the data. And so this is the major feat of this upgrade, is that we've been able to not only color code the data as we're used to seeing for years, but now we can also interact with the underlying data and get a clue as to what the numbers actually are. So yeah, I showed you timescale updating here, boundary updating here. Let's take a look at the other maps that you can download here. So the dashboard will show you the most recent months that we have of data. We update the data monthly. These are these are PRISM monthly data, and we get those data updates around the 5th of each month. So February data should arrive March 5th. But archive data is available through our product selector. And so we just click on new map and you get 3 different ways to look at a map. Contour maps are pure SVG maps, so they look really sharp, but you have some limitations. Let's look at something in the region here. So let's look at Oregon, and let's look at PDSI. So the current one will show you what essentially is on the dashboard. If you want to look at an archive, you can go back. Let's take a look at last year. And then let's take a look at February. And then you can choose the particular planar projection you want. Albers is what we're looking at on the dashboard. If you wanted to see a Web Mercator one, it will be it there. And this is also interactive, so you can click on these levels here, and it will show you, the color coordinated region there, so you can confirm that the numbers are representative of the correct binning. These can be pretty nice to display because they scale very nice in presentation. This is a nice opportunity to also show that you can interact with the result. Obviously, you can click and get data on the region, but then you can also save the output as a PNG or an SVG. Both formats essentially cannot support interactivity. So as soon as you save it, you'll have a flat map. I'm clicking on it right now, and there's obviously nothing happening. So the interactivity is really just alive in the browser, and that's it. You can also save it as SVG. SVGs are really nice for poster presentations if you want really large maps, but you don't want that pixelated look and feel. SVG is the way to go. And then you can also get to the underlying data in either a GeoTIFF format or a NetCDF format. The data are continental US, so it doesn't matter what subregion you select, you always get the full data set for any analysis you want to do downstream. So that is the contour map. The other, what we're looking at here is a discrete pixelated map. You can also roll an archive of this using a discrete color scale by clicking the third option here. Let's pick Idaho, and let's do SPI. Got a lot of time scales here that you can choose from. Let's do an annual one. Let's go back to 2014, for example. And then let's use the default projection here. And you can see another interactive map here. So you can look at the actual SPI indice values. And the continuous color scale, so if you're interested in more of a nuanced color dispersion, the continuous color scale will give you that. So let's compare SPI 12-month 2014 and February and Mercator. So you'll see a little cloudier color dispersion, and that will, if you're interested in some of the finer points of analysis there, and you don't want the discrete to bend things unjustifiably, or if you're interested in some more nuanced analysis, this is an option that's available to you as well. So our plan for rolling out archives and charts and tables, right now, we have links to the legacy Westwide Drought Tracker. So if you're interested in the time series analysis, you have this old user interface. We have plans to bring all this nice time series information over to the new format. And the large scale data archive is also in development, where you can roll up many GeoTIFFs or NetCDFs if you want to do a more extensive analysis on the complete data set or some major chunk of it. But yeah, that's all I wanted to show today. Thank you for your time, and I'll turn it back over to Britt.
Great, thank you, Justin. Let's see, there's a couple questions in the chat box, and keep adding those in. One was, when will the next drought outlook be released? And that should be March 16th. So those are released the third Thursday of every month. And then I think we had a question. Whoops, hold on one second. Looks like we had a question for Janelle. about can you show the sweet spot that covers a particular sub-basin?
I don't think I quite understand what the question's asking.
Yeah, I'm wondering if it's saying, is there a way with some of the like the NRCS tools to maybe understand where the measurements are being taken that are then used to show the data for a sub-basin? I'm not sure. And if you can follow up with more details, we're happy to try to answer that question. And are there...
On so the water year graphs are updated. Like that's one way to look at different stations because the sites are each put into a water year graph. So those are one way. Another way, if this is answering the question, the percent of normal map also does show, like you can sort by basin, not by basin, but by snow tell site. And you should be able to look at each individual snow tell site and what the data says for those snow tell sites.
Okay. She followed up, when the SWE names are not lined up with a tributary, e.g. the Willamette Basin, how do you know which trib is matched to the SWE?
I can look into that. I don't have an answer at this moment in time, but I can try to find that out.
Yeah, great. Thank you. And Anne will definitely follow up with you on those questions. Any other questions before we wrap up today? We have the contact information for the speakers up on the screen, and our next webinar will be April 24th, so mark your calendars. I don't see any other questions coming in, so we'll go ahead and wrap up. Oh, let's see, there might have been a hand raise. Oh, just a big thank you to all the presenters, and agree with that. Thank you, we couldn't do this without you. Okay. Well, thank you everyone so much, and we'll see you in 2 months. Take care.